Hey everyone, this is Connor Mead with the Calculation Center, and this is another video in our linear algebra series. This time we'll be talking about finding the eigenvalues and eigenvector for 3x3 matrices. Now the idea for doing this is roughly speaking the same thing as for the 2x2 matrices, except we're going to see that some of the steps are a little more difficult. Now let's just reiterate what the idea is on how we find eigenvalues in general. And it goes like this. First, we compute the characteristic polynomial of A, Ca of lambda, which is defined to be the determinant of A minus lambda times the identity. The second step is to find the roots of this cubic polynomial, lambda 1, lambda 2, and lambda 3. Notice that there'll be 3 of them this time because we're dealing with a 3x3 matrix. And again, of course, the roots of Ca of lambda are just those numbers, which when you put them into Ca of lambda, you get out 0. And the third and final step is to solve a system of linear equations, each corresponding to one of the roots. So we'll have to solve one for lambda 1, one for lambda 2, and one for lambda 3, with the formula given here. Now, the important thing to notice here is that steps 1 and 3, I have little ticks next to them here. That's because they're about as easy as they are in the 2x2 case. You know, this calculation's a bit longer, and you have to solve an extra system of linear equations down here, but effectively these things are the same thing, and so won't be the focus on this video. The focus on this video will be finding the roots of the cubic polynomial. Normally, this is really too hard to do on paper. So if we're given this question in an exam or something like that, we should expect that we'll get extra info or a clue to guess or something like that. Okay, and I've written down an example of such a clue. Here we've given a matrix 3, 2, minus 3, 0, minus 1, 3, and 1, 3, minus 2. And we want to find the eigenvalues, given that lambda equals 2 is an eigenvalue. So we're given one of the eigenvalues, we're kind of trying to find the other two. Now, recall that Ca of lambda is the determinant of this object, this matrix here. I'll go through it quickly again, but if you have trouble computing the determinant of a 3x3 matrix, I recommend going back and checking out the video we've already done on this topic. So we take the top left entry and take the determinant of the submatrix that's left over when you just take these 4 elements. So minus 1. Well, let's do it a little faster just because we have a lot to get through here. So it's minus 1 minus lambda times minus 2 minus lambda minus 9. That's just doing the determinant out, the subdeterminant, I should say. And we're going to write down a minus sign, go to the next topic, the next entry, I should say, and take the determinant of 0, 3, 1, minus 2 minus lambda. The 0 will kill off one of these terms, so it'll just be minus 3. And lastly, we'll get the minus 3 times the determinant of this matrix here, and that'll just come out to be 1 plus lambda. So let's multiply this all out. So we'll get out here 2 plus 3 lambda plus lambda squared minus 9 plus 6 minus 3 minus 3 lambda. Multiplying up these brackets together as well, we get 6 minus 3 lambda squared minus lambda cubed. Oh, let's do this a little more carefully, I guess. Better than there. So this will actually become plus 9 lambda plus 3 lambda squared minus 27. That was just because I got a little confused in the order I was doing the multiplication, so I just wanted to redo it there more carefully. But now going through it, so this is the 3 being distributed through this bracket. Now to distribute the minus lambda, we get minus 2 lambda, minus 6 lambda squared, minus lambda cubed, plus 9 lambda. And we get on the outside a plus 3 minus 3 lambda, just coming from this bit here. So let's just gather up all our terms, and we'll get a minus lambda cubed. How many squares have we got? Our squares will... This right? No, sorry, there's a mistake here, I believe. Yeah, this should have been a minus 3 lambda squared, not a 6 lambda squared. Sorry, I made a mistake in distributing out the lambda there, but is this all right aside from that? Yeah, it all looks fine. So minus lambda cubed, we got 3 lambda squared and a minus 3 lambda squared, so these will cancel, so we get a plus 0 lambda squared. Obviously, you don't have to keep track of this, but it'll be useful later on for us. For our degree 1 terms, we got a 9 lambda, total 7 lambda, total 16 lambda, total 13 lambda, just adding up all these terms. And lastly, we get a 6, a minus 21 total, and a plus 3 is a minus 18 total. So this is our polynomial. Now, like I say, this is in general very hard to solve for its roots. If I just gave you this polynomial, I wouldn't expect anyone to be able to solve for its roots by hand. But given that we know lambda equals 2 is a root, and this can be verified by substituting in lambda equals 2 here, and you'll see that you get out 0. But lambda equals 2 as a root also implies that lambda minus 2 is a factor. Okay, that's to say we can divide it in evenly to write this cubic as a product of two other polynomials. So let's do polynomial long division here. So we get lambda minus 2, and we're putting it into minus lambda cubed plus 0 lambda squared plus 13 lambda minus 18. Let's give myself a little more room as well. And in case you haven't seen this in a while, I'll just go over it briefly. You just basically want to keep on looking at this term and comparing it to various terms here and seeing what you have to multiply this term by to get to this term. So this first instance, for example, to get lambda to minus lambda cubed, you multiply it by minus lambda squared. So then what you do is you multiply this entire bracket here by minus lambda squared and write it down here. So you get out a minus lambda cubed plus 2 lambda squared. Draw a bar and subtract these two elements from each other. So these two things cancel and we get a minus 2 lambda squared here. From here, you then write down plus 13 lambda and iterate the process. So we look at what we need to multiply lambda by to get to minus 2 lambda squared. It's obviously minus 2 lambda. So you get minus 2 lambda squared plus 4 lambda. Draw your line, subtract off. And we'll get 9 lambda here, minus 18. And to get 9 lambda from lambda, you have to multiply by 9. And we'll actually see this is the sign that you actually do indeed have a proper factor. If this doesn't work out at the end, you've made a mistake. But since we get the same things here, these things cancel perfectly. And that's a sign that we've done our factorization correctly. Now what this means is that CA of lambda, which was originally equal to minus lambda cubed plus 13 lambda minus 18, the thing I wrote down here, this thing can actually be written as lambda minus 2 times minus lambda squared minus 2 lambda plus 9. And furthermore, it's actually quite easy to solve the roots for this polynomial now. I'll leave that as an exercise because it's just applying the quadratic formula. But we can then conclude that lambda 1 is equal to 2, as we knew. And once we get the two factors from this, or the two roots, they're the same thing really, we'll see that lambda 2 is equal to minus 1 plus root 10, and lambda 3 is equal to minus 1 minus root 10. And just to see this, remember, just use the quadratic formula on this expression here inside the second bracket. Okay, so that's how we get the other two roots, given that we only had one, but we get the other two by dividing in the one we know. Okay, this factor that corresponds to our root. Okay, now for a slightly different approach, we're going to assume we've been given the same problem with slightly different information. So we want to find this eigenvalues of A, which is now a new matrix, minus 1, 1, 0, 1, 2, 1, 0, 3, minus 1. And we know all the eigenvalues are integers, that is, they're whole numbers, positive or negative whole numbers. Okay, so I'm going to skip through the characteristic polynomial this time, because I've already gone ahead and done it beforehand. But this is out here if you guys need to go over it and check your work versus it. But we end up with this characteristic polynomial. Now, how do we find the roots of this polynomial, given that we know all the roots are integers? Well, the idea is, instead of checking, maybe we could just keep on trying a load of low integers, but we actually can do better than that. Because roots being integers, so roots are integers, implies that roots are factors of the constant term. Okay, and in our case, this constant term, we just mean 6, which is this term here. It's the term without any lambdas in it. So that means the possible candidates for roots are 1, minus 1, 2, minus 2, 3, minus 3, or 6 minus 6, because these are the only numbers, the only integers which divide 6. And now all we need to do is substitute in these values into the equation minus lambda cubed plus 7 lambda plus 6 and see which ones are zeros. For example, when lambda equals 1, we get out minus 1 plus 7 plus 6, that's 12, and it's not 0. So lambda equals 1 is not a root. However, when we put in minus 1, the first term becomes 1 minus 7 plus 6, and this is indeed 0. So therefore, this is actually a root. Let's try lambda equals 2. We get minus 8 plus 14 plus 20. That's 12 again, so not a root. Minus 2 will get us 8 minus 14 plus 6, which is a root, actually. So lambda equals 2 is a root. Lambda equals 3 will get us minus 27 plus 21 plus 6. So that is indeed, again, 0. Now, as I said earlier, cubics can only have 3 different roots at most. So we actually know these are the 3 roots, so we can stop here. But, substituting in these values will get you non-zero numbers as well. So therefore, we would conclude the roots are lambda 1 equals minus 1, lambda 2 equals minus 2, and lambda 3 equal to plus 3. And these are our roots. Our roots of the characteristic polynomial, and hence our eigenvalues of the matrix. As a little side note, if we had only known that one of the integers were an eigenvalue, this method would not have worked, because we can't then assume that this last term is a factor we can't assume that the roots divide the constant term in that case. Necessary. There's a little more work you have to do, basically. But anyway, hopefully that made sense to everyone. This was Connor Mead with the Calculation Center, and I'll see you guys next time.